Hi everybody, welcome back. Hope you all did good on your test. We are going into a new chapter, section 6.1, and this is going to move us on beyond triangles and into polygons. So we'll start a little bit by talking about polygons and then triangles and then polygons, and hopefully you have a memory of all those kind of things. And then we're going to hit really hard into quadrilaterals, specifically getting into parallelograms to start off with. So these next few sections are going to be a little bit diverse. This first section is about polygons in general, and then we'll dip into parallelograms for the next few sections. So we're in section 6.1. We're going to talk about the angles and the measures of interior and exterior angles in all polygons. Okay, give you a few formulas that work with those. All right. So, big question, why does the sum of the interior angles of a polygon depend on the number of sides, and the sum of the exterior angles of a polygon don't? All right, so we'll talk about equilateral polygons, equiangular polygons, and regular polygons, and let's get it going. So, talking about interior angles of polygons, here's what we mean. First of all, quick review. What is a polygon? A polygon is a closed figure in one plane, and it's composed entirely from line segments. So what you will see over here are a bunch of examples of polygons. You see they are all in one plane. They are all closed, no open spots, okay? And they're entirely made of straight lines. The examples of things that are not polygons is anything with a curve, anything that's not closed. So just generally this is what you got. Polygons, not polygons. We're going to be talking about polygons. All right, going back, our first kind of polygon that we learned a lot about, remember triangles. Well, you had better remember triangles. Specifically, remember about all three of those inside angles. We may not know exactly what they are in this picture, but we do know that no matter what, the angles of a triangle, all three of them have to add up to 180 degrees. The sum of the angles, interior angles of a triangle have to add up to 180. All right, how about other polygons? Well, here's something kind of cool. I've just put some random polygons here on this paper, and let's make some lines in them and see if we can figure out what is the sum of the angles in any polygon. All right, so we'll start with a quadrilateral, a four-sided figure. And some of you, I'm sure, already have this memorized, that a quadrilateral, the sum of the angles has to be 360. Or in other words, we got 1, 2, 3, 4 angles. We know they all add up to 360. But how do we get that? Let's look at something kind of cool. We're going to look at making some lines here. Okay, look at what happens when I make a diagonal in that one polygon. If it has four sides, quadrilateral, and I make a diagonal, look what we've done. I've created 1, 2 triangles. Both of those triangles have to add up to 180, right? Have to have angles that add up to 180, and I've got 2 of them. Therefore, 180 plus 180, the sum of those angles makes 360. Okay, so for a four-sided figure, I can draw one diagonal, split it into 2 triangles, and those 2 triangles end up looking like this. 2 times 180 add up to 360. All right, how about a 5-sided figure? So I've got a pentagon right here. Let's make a couple diagonals. There's 1, there's 2. And look what we got. We now have 3 triangles. I didn't want to do that. Let's go back here. 3 triangles. There's a 180. There's a second one. And there's a third one. So for a 5-sided figure, I'm going to end up with 3 times 180. And that's going to make 540 degrees in any 5-sided figure. All right, check out the pattern we're going to be seeing now. Six-sided figures. One diagonal, 2, 3, and we have 4 triangles. See the pattern coming on? 4 times 180 is going to give us, what is that? 720. All right. So a six-sided figure, I think that's what I got here. Triangle 1, 2, 3, 4. So that's 1, 2, 3, 4, 5, 6. That's a seven-sided figure. So we end up with, this was our six-sided figure. All right, I'm catching my train of thought here. Six-sided figure. I ended up with 4 times 180. If it had 6 sides. If it has 7 sides, 5 times 180. See the pattern. What do you guess is going to happen for this 1, 2, 3, 4, 5, 6, 7, 8-sided figure? Well, if our pattern holds true, we should end up with 6 triangles when we split it up this way. And the total of all of the angles, when we add them up, all of the triangles, is going to be 1, 2, 3, 4, 5, 6 times 180. So, what we're seeing is that the number of sides, well, if I had 4, I subtract 2 and multiply that by 180. If I had 5, subtract 2 times 180. 6, subtract 2. 7, subtract 2. 8, subtract 2. In fact, for any polygon, look what happens. 4 sides, 2 triangles, 360. 5 sides, 3 triangles, 540. 6 sides makes 4, 720. 7 made 5. 8 made 6. And the numbers come out to be whatever that n minus 2, the number of sides, subtract 2. So therefore, check out a 20 gone. It would make 18 triangles. The sum of my angles would have to be 18 times 180. Any polygon, the sum of the measures of the interior angles for any number, n minus 2 times 180. All right, so here's a couple for you to try on your own. Pause if you like. Answers coming shortly. All right, so a 36 gone. N is 36. Plug that in. Subtract 2. Multiply by 180. There's the sum of our angles. Going backwards, a certain polygon has angles that add up to 2520. How many sides does it have? We're going to plug it into that same formula. Right? N minus 2 times 180 must be 2520. Divide by 180. Add the 2. It must be a 16-sided figure. All right. Hope that makes sense. Now, another kind of problem. Look at, this is polygon angles. All right. It's a hexagon, 6 sides. Find the measure of angle G. See that everything is labeled except for G. So, pause. Here comes the answer. All right, since it's a hexagon, the sum of all the sides of all the angles must be 6 minus 2 times 180, or 4 times 2, 4 times 180 equals 720. So, therefore, I need to add up all 6 angles and get 720. There's my unknown. I'm using G as the variable. When I add them up, we come to find out, combine those like terms. These all add up to 595. Plus G must be 720. G has to be 125 to make this work out so that they all add up to what they need to add up to, 720. Okay. A couple more definitions here. Okay, different kinds of polygons. An equilateral polygon, I think we know from before, an equilateral means it's got side lengths that are all the same. So all these figures here are examples of polygons that are equilateral. All right? Equiangular, looking at the other side, are polygons that have all angles the same. So this would have 6 angles that are all the same. This would have 4 of them. All right? So those are equiangular. Now this little box here, little overlapping area, if a polygon is both equilateral and equiangular, we call it a regular polygon. So these are examples of regular polygons. Sides are congruent, angles are congruent. It is both equilateral and equiangular. So is this shape here, we call that a square. Okay. The rest of these would be referred to as a regular octagon, a regular pentagon, a regular hexagon, all right, depending on the number of sides. All sides are congruent, all angles are congruent. That makes it a regular polygon. So let's talk now. There's a corollary to that, the last theorem that we learned about. If the measure of all of those angles adds up to n minus 2 times 180, and they're all the same, we can divide by the number of sides to find out the measure of any interior angle, just one of them, of a regular n-gon. Example is, I got a regular octagon right here. Okay? What's the measure of any one angle? Well, here's how we're going to find it. We know that the total of all of them has to be 6 times 180. Well, if we divide that by 8 of them that all have to be the same, basically you use this formula back here, right? Total of all the angles divided by how many there are. It should tell us what each one of those are because they're all the same. So, n minus 2 times 180 divided by n is 8 because we've got an octagon. So, 8 minus 2 times 180 divided by the 8 different angles. Each one of those is 135. Okay? The measure of any single angle in a regular 50gon. Here comes the answer. Pause. Oops. Here comes the answer. Pause it if you like. Here it comes. All right. N is 50. So we're going to do 50 minus 2 times 180 divided by 50. We end up with 172.8 degrees in any one of those angles. All right. Let's talk exterior angles for a moment. Remember exterior angles. We've talked about them before with triangles. We hopefully remember a theorem that said that this angle here, angle 1, has to equal the sum of 2 and 3. But, not going to be that fancy with the other polygons, but we can make exterior angles around any polygon. The angles I'm marking here around the quadrilateral are exterior angles. So are these around the pentagon, and these around whatever that is, an octagon, I think. Okay, these are called exterior angles. They are formed by a straight line that is an extension of a side of the polygon. All right, so all of these extend the side, and we form what's called an exterior angle. All right, check out the angles in hexagon from before. So this is check out the angles in hexagon known as angles from before. All right, so this is the same picture we had before. And we're going to be looking at extending these out, and looking at, it's not quite pretty as it's going to be, and looking at exterior angles, all right? And I've done the work over here. We have these lines extending out. You notice the exterior angles here are, pick another color, go purple. Exterior angle there is 60, 30, 55, because of course, remember, we've all got linear pairs being formed by all of these straight lines. They all have to add up to 180. So there's 85, there's 40, and that one's got to be 90. So those are the 6 exterior angles. Look what happens when we add them up. They add up to 360. All right? I could show you the same thing for any other polygon. Quadrilateral, pentagon, octagon. In fact, for any polygon, the sum of the exterior angles, one at every vertex, must be 360. Exterior angles always add up to 360, no matter how many of them there are. So, question for you. Pause. Here we go. Answer coming. We got what is the measure of angle 1 in this regular octagon? Well, it's an octagon, so we know all 8 interior angles are congruent. Since they all form identical linear pairs, every exterior angle must be congruent. In other words, since they all add up to 360 now, everyone is congruent. I can divide it by 8 of them, and I know every one of these exterior angles would have to equal 45. Okay, that's it. I will see you guys tomorrow.